In the final years of the 1960s, the balance of global power rested not only on diplomacy or ideology, but on physics. Altitude, speed, radar frequency, fuel flow, and metal fatigue became the invisible variables that defined survival. The United States found itself locked in a strategic contest where deterrence depended on the ability to deliver nuclear force under the most hostile conditions imaginable. Intercontinental ballistic missiles promised speed, but they were predictable. Submarine-launched weapons offered stealth, but their numbers were finite. What remained was the bomber, flexible, recallable, and symbolically powerful. Yet by the end of the decade, the bomber fleet that had once embodied American air dominance was aging, vulnerable, and increasingly obsolete. The B-52 Stratofortress, despite its range and payload, was designed for a world where altitude equaled safety. Soviet surface-to-air missile networks shattered that assumption. The downing of high-altitude reconnaissance aircraft proved that speed alone could no longer guarantee survival. Penetration would now require something different. Not just faster aircraft, but aircraft that could disappear into the terrain, outrun interceptors, and adapt to radically different mission profiles in a single flight. The future bomber would need to fly higher than some fighters, lower than mountains, faster than missiles, and farther than any aircraft of its class. It would need to do all of this while carrying the most destructive weapons ever built. This was the environment that gave birth to the concept of a new American strategic bomber. The requirement was brutally clear. The aircraft had to penetrate deep into Soviet territory, evade layered defenses, and deliver nuclear weapons with precision. It had to survive not by brute force alone, but by exploiting the physics of radar, terrain masking, and speed. Engineers quickly realized that no fixed-wing design could satisfy such contradictory demands. Long-range cruise required efficiency and lift. Supersonic dash demanded swept wings and structural strength. Low-altitude penetration required stability, shock resistance, and extraordinary pilot workload tolerance. The solution, at least on paper, was a wing that could move. Variable geometry wings were not new, but never before had they been proposed for an aircraft of this size, mass, and mission importance. By sweeping the wings back, drag could be reduced at supersonic speeds. By extending them forward, lift and fuel efficiency could be maximized for takeoff, landing, and long-range cruise. In theory, a single aircraft could behave like several entirely different machines depending on the phase of flight. In practice, this meant designing one of the most mechanically complex airframes ever attempted. The program that emerged was ambitious even by Cold War standards. It demanded advanced materials capable of withstanding repeated high-speed, low-altitude flight. It required engines powerful enough to sustain supersonic speed, yet efficient enough to cross continents. Avionics had to integrate terrain-following radar, inertial navigation, and weapons systems with unprecedented reliability. Every subsystem pushed the limits of what was technologically feasible at the time. Failure was not an option, yet risk was unavoidable. From the very beginning, the aircraft that would become known as the B-1 was more than a machine. It was a strategic statement. It embodied the belief that engineering ingenuity could outpace any defensive system. It reflected a confidence that complexity, if properly managed, could be transformed into dominance. But it also carried the weight of political expectation. Billions of dollars were committed before the aircraft ever flew. Its success or failure would influence not only military doctrine, but national confidence in large-scale technological programs. As design studies matured, the aircraft grew in size, weight, and cost. Engineers were forced into constant compromise. Strength added mass. Mass demanded more thrust. More thrust increased fuel consumption. Fuel added weight, which in turn stressed the wing pivot mechanisms that defined the aircraft's identity. Each solution created new problems, cascading through the design like shockwaves. The aircraft was no longer just a bomber. It was an ecosystem of interdependent systems where no decision could be isolated. Low-altitude penetration became the defining mission, and with it came a brutal operational reality. Flying at high subsonic or supersonic speeds only a few hundred feet above the ground subjected the airframe to continuous turbulence and stress. Unlike high-altitude flight, where air is relatively smooth, the lower atmosphere is chaotic. Gusts, Thermal currents and terrain-induced airflow variations battered the structure relentlessly. This was not a short dash, it was hours of sustained punishment. Engineers had to design for fatigue life far beyond any previous bomber, while pilots faced a mission profile that allowed little margin for error. The political environment surrounding the program was just as turbulent. As costs escalated, scrutiny intensified. Critics questioned whether such an expensive aircraft was necessary in an era increasingly dominated by missiles. Others argued that advances in air defense would inevitably negate any bomber, regardless of its speed or altitude. Meanwhile, arms control negotiations introduced uncertainty. Treaties were drafted around assumptions of bomber capability, and the aircraft became entangled in diplomatic calculations that had little to do with aerodynamics. Despite these pressures, the vision remained compelling. The aircraft promised unmatched flexibility. It could take off with wings extended, carrying heavy fuel loads. It could cruise efficiently across oceans. As it approached hostile airspace, it could sweep its wings back, descend to low altitude, and accelerate, using terrain as a shield. In the final phase, it could dash at supersonic speed, release its payload, and escape before defenses could react. No existing bomber could offer such a profile. Yet the very features that made the aircraft extraordinary also made it fragile as a program. Complexity increased maintenance demands. Weight growth eroded performance margins. The variable sweep wing, while elegant in theory, introduced mechanical vulnerability and inspection challenges. Every pivot, actuator, and bearing became a critical point of failure. The aircraft demanded a level of logistical support that rivaled its operational sophistication. By the time the first prototype approached readiness, the world it was designed for was already shifting. Defensive systems evolved. Radar coverage improved. Interceptor capabilities expanded. At the same time, stealth technology began to emerge, offering a radically different solution to the penetration problem. Instead of outrunning or overpowering defenses, stealth proposed avoiding detection altogether. This philosophical divergence would prove decisive. Still, the aircraft represented a triumph of engineering ambition. It was not conceived as a compromise, but as a bold attempt to dominate every regime of flight relevant to strategic bombing. Its designers believed that adaptability was the ultimate weapon. In that belief, they captured the spirit of an era defined by confidence in technology as a solution to existential threat. As the program moved closer to flight, the stakes became undeniable. Success would validate decades of investment and reaffirm the bomber's role in strategic deterrence. Failure would raise uncomfortable questions about the limits of complexity and the cost of ambition. The aircraft stood at the intersection of physics, politics, and philosophy, a machine shaped as much by human belief as by metal and fuel. What followed would test not only the airframe, but the assumptions that created it. The first flight would mark not the end of uncertainty, but its transformation. The aircraft would leave the ground carrying the hopes of its engineers, the expectations of its sponsors, and the burden of a strategic doctrine already under pressure. The sky it entered was unforgiving, and the future it faced was anything but certain. As testing expanded beyond paper studies and wind tunnels, the aircraft's true nature began to reveal itself. What had once been an elegant solution on drafting tables became a relentless engineering trial in the real world. The bomber was no longer an abstract concept. It was a living structure subjected to forces that exposed every assumption made during its design. Each test flight was not merely an evaluation, but an interrogation of the aircraft's philosophy. At the heart of the challenge was the decision to prioritize low-altitude, high-speed penetration. This mission profile demanded something unprecedented from a strategic bomber. Unlike fighters, which could rely on agility and short exposure times, the bomber had to endure sustained stress for hours. Flying close to the ground at high speed meant the aircraft constantly encountered dense, uneven air. Turbulence that would be insignificant at altitude became violent near the surface. Shock loads propagated through the wings, fuselage, and engine mounts, accumulating fatigue at a rate that shocked even experienced engineers. The variable geometry wing, the aircraft's defining feature, became both its greatest asset and its most complex liability. The wing pivot mechanism had to transmit enormous aerodynamic loads while remaining precise enough to ensure symmetrical sweep. Any imbalance could induce dangerous roll moments. The structure surrounding the pivot had to be massively reinforced, adding weight precisely where engineers least wanted it. Maintenance crews soon discovered that inspecting and servicing this system required extraordinary effort, time, and specialized equipment. Then there were the engines. The bomber required power plants capable of sustained supersonic dash, yet efficient enough for intercontinental range. This dual requirement forced compromises in compressor design, turbine materials, and fuel control systems. Engine performance was impressive, but reliability under the brutal low-altitude profile proved elusive. High power settings combined with ingestion of debris and turbulent airflow accelerated wear. Every maintenance cycle revealed components operating closer to their limits than anticipated. Avionics introduced another layer of risk. Terrain-following radar was essential for low-altitude penetration, allowing the aircraft to automatically maintain a precise clearance above the ground. This system had to process terrain data in real time while commanding flight control inputs with absolute reliability. Any error could be catastrophic. Integrating this radar with navigation, autopilot, and weapons systems demanded software complexity that pushed the boundaries of what was achievable in that era. Unlike modern digital systems, much of this integration relied on analog components and early digital logic, increasing susceptibility to failure. Financial risk grew in parallel with technical risk. Each new solution required funding, and each funding increase invited political scrutiny. The program's budget swelled into the billions, becoming a visible symbol of Cold War expenditure. Supporters argued that deterrence justified any cost. Critics countered that the aircraft represented diminishing returns, consuming resources that could be better spent elsewhere. The bomber was no longer judged solely on performance, but on its perceived value within a rapidly evolving strategic landscape. Strategic doctrine itself was shifting beneath the program. Missile technology matured rapidly, offering faster response times and reduced vulnerability. Submarines armed with ballistic missiles provided stealth and survivability unmatched by any aircraft. In this environment, the bomber's role was questioned. Why invest in a manned platform exposed to defenses when unmanned weapons could strike with near certainty? The answer, according to proponents, lay in flexibility. A bomber could be recalled. It could signal intent without immediate destruction. It could adapt to changing circumstances in a way missiles could not. Yet this argument struggled against the bomber's growing complexity. Flexibility in mission profile came at the cost of inflexibility in logistics. The aircraft demanded long preparation times, extensive ground support, and highly trained crews. Its operational readiness rate lagged behind expectations. Each additional hour of flight translated into significant maintenance effort. In a crisis scenario, the question was not only whether the bomber could penetrate defenses, but whether it could be generated in sufficient numbers quickly enough. Arms control negotiations intensified these doubts. Treaties aimed at limiting strategic weapons forced policymakers to consider how each platform was counted and constrained. The bomber's speed, payload, and penetration capability made it a focal point in diplomatic discussions. Its very existence influenced negotiation positions, turning engineering decisions into bargaining chips. The aircraft was now entangled in geopolitics at the highest level, subject to forces far removed from aerodynamic equations. Within the engineering teams, morale fluctuated between pride and exhaustion. Achievements were undeniable. The aircraft demonstrated remarkable performance envelopes. It could transition smoothly between flight regimes that once required entirely different airframes. Pilots reported a machine that felt powerful, responsive, and unlike anything they had flown. Yet these successes were shadowed by persistent issues, structural fatigue concerns, escalating maintenance demands, and the constant pressure to justify cost overruns. The risk was not only financial or political, but philosophical. The aircraft represented a belief that dominance could be achieved through mastery of complexity. It assumed that adding capability, even at great cost, was preferable to simplifying the problem. This belief had served aerospace engineering well in the past, producing aircraft that defined eras. But the emergence of stealth technology challenged this assumption. Instead of confronting defenses with speed and power, stealth sought to render them irrelevant. As stealth concepts matured, comparisons became unavoidable. A stealth aircraft promised penetration without the need for supersonic dash or low-altitude punishment. It suggested a future where radar invisibility mattered more than raw performance. In this comparison, the bomber began to look like a masterpiece from an era already ending. Its strengths were undeniable, but they addressed a problem that was being redefined. Still, canceling such a program was no simple decision. The aircraft embodied years of work, thousands of jobs, and a vast industrial network. Entire communities depended on its continuation. Ending the program would ripple through the aerospace sector, affecting suppliers, engineers, and strategic planning alike. The bomber had become not just a weapon, but an economic force. As flight testing continued, data accumulated relentlessly. Engineers refined fatigue models, adjusted operational limits, and introduced modifications to extend service life. Each fix demonstrated ingenuity, but also underscored the aircraft's fragility as a concept. It could perform its mission, but only within carefully managed parameters. The margin for error, whether technical or political, was shrinking. The aircraft stood at a crossroads. It was proving that the original vision was technically achievable, yet it was also revealing the cost of that vision. The question was no longer whether engineers could make it work, but whether the world it was designed for still existed. The answer to that question would determine not just the fate of the bomber, but the direction of strategic aviation itself. By the time the aircraft entered the public eye, it carried an identity shaped as much by expectation as by metal. The rollout was staged as a declaration of technological confidence. This was not merely another bomber. It was presented as the embodiment of American aerospace supremacy. The aircraft's massive frame, aggressive lines, and sweeping wings conveyed power and adaptability. On the surface, it appeared to fulfill every promise that had justified its creation. The first flights confirmed much of what engineers had predicted. The bomber demonstrated impressive acceleration and range. Its variable geometry wings transitioned smoothly between configurations, validating years of design work. At altitude, it behaved with the stability expected of a strategic platform. At low level, it proved capable of maintaining high speed while following terrain with precision. For a brief moment, it seemed that ambition had triumphed over doubt. Yet flight testing also transformed theoretical concerns into measurable realities. Structural fatigue emerged as a dominant issue. Data showed that the stresses imposed by prolonged low-altitude flight were far more severe than initial models had predicted. The airframe was being consumed by its own mission profile. Engineers recalculated service life projections and discovered that, without modification, the aircraft would require extensive structural reinforcement or sharply reduced operational limits. Both options carried significant cost. Operational doctrine was forced to adapt. The bomber's original concept envisioned frequent low-level penetration missions, exploiting speed and terrain to evade defenses. Reality dictated caution. Restrictions were imposed on how often and how long the aircraft could fly at extreme profiles. Supersonic dash, once a cornerstone of survivability, became a limited capability rather than a routine tactic. Each concession preserved the airframe, but eroded the purity of the original vision. At the same time, the strategic environment continued to evolve. Advances in radar processing, sensor fusion, and interceptor performance reduced the effectiveness of speed-based penetration. Defensive systems became more resilient, less dependent on single radar frequencies, and more capable of tracking fast-moving targets at low altitude. The bomber's advantage narrowed. It was still formidable, but no longer revolutionary. The program's cost profile became increasingly difficult to defend. Each modification required funding. Each funding request triggered renewed debate. Decision-makers faced an uncomfortable calculus. Continue investing in an aircraft whose mission was being undermined by technological change, or redirect resources toward emerging concepts that promised greater long-term relevance. The bomber had become a case study in sunk cost versus future value. This tension reached its peak as stealth aircraft moved from concept to reality. Early demonstrations showed that shaping and materials could dramatically reduce radar signature. Instead of outrunning defenses, an aircraft could slip through them. The implications were profound. If detection could be delayed or avoided entirely, the need for extreme speed and low-altitude punishment diminished. The bomber's defining strengths suddenly appeared misaligned with the future of air warfare. Politically, the aircraft found itself vulnerable. Its cancellation would signal a shift in priorities, but also invite accusations of wasted investment. Supporters emphasized that the bomber was already built, already flying, and already capable. They argued that abandoning it would leave a gap in strategic capability and damage industrial expertise. Opponents countered that continuing the program would lock resources into a platform optimized for a fading doctrine. The debate was not merely technical, it was philosophical. The bomber represented an era when supremacy was achieved by pushing performance to extremes. Speed, altitude, and payload were the metrics of success. Stealth proposed a different hierarchy, where invisibility outweighed raw power. The aircraft sat uneasily between these worlds, a machine designed for yesterday's threat environment and tomorrow's budget constraints. Ultimately, the decision reflected compromise rather than absolutes. The original configuration, optimized for supersonic penetration, was deemed too costly and strategically misaligned. The aircraft would not disappear, but it would be transformed. Its mission shifted away from nuclear penetration toward conventional strike. Supersonic dash became secondary. Low-altitude flight was reduced. The bomber evolved into a platform for delivering precision weapons from standoff ranges, leveraging payload and range rather than speed alone. This transformation was both a rescue and an admission. It preserved the aircraft's relevance, but at the cost of its founding ambition. The bomber no longer embodied the ultimate penetration solution it was conceived to be. Instead, it became a highly capable, but fundamentally different, instrument of power. In this role, it proved effective, participating in conflicts that demonstrated its ability to deliver sustained conventional firepower with precision. From an engineering perspective, the aircraft story became one of adaptation. The variable geometry wing, once essential to its mission, remained a defining feature, but its operational importance diminished. Maintenance demands remained high, but manageable within a revised concept of operations. The bomber found a niche that justified its existence, even if it fell short of its original promise. Economically, the program left a complex legacy. It sustained an industrial base and preserved critical skills. It generated employment and technological spin-offs. Yet it also served as a cautionary tale about escalation of complexity and cost. Future programs would be scrutinized through the lens of this experience, with greater emphasis on adaptability and alignment with long-term strategy. Culturally, the bomber occupied an ambiguous place. It was admired for its presence and performance, respected by crews who flew it, and recognized as a symbol of Cold War ambition. At the same time, it was often cited as an example of overreach, a machine that pushed too far in pursuit of a solution that the world outgrew before it could be fully realized. In this sense, the aircraft did not fail in the conventional meaning of the word. It flew, it fought, and it served. Its failure was conceptual. It failed to define the future it was meant to dominate. The world moved in a different direction, and the bomber followed as best it could. The story of its transformation underscores a central truth of aviation history. Success is not measured solely by performance, but by timing. An aircraft can be brilliant and still arrive too late or aim at the wrong problem. The bomber's journey from revolutionary penetrator to adaptable strike platform reflects the relentless pace of technological and strategic change. As the aircraft settled into its revised role, its influence persisted. Engineers studied its strengths and weaknesses. Strategists examined its evolution. Designers of future aircraft absorbed its lessons. In this way, the bomber's impact extended beyond its operational life, shaping decisions long after its original mission had faded. The machine that once promised to outrun and outfly every defense became a reminder that innovation must anticipate not only what is possible, but what will endure. As the aircraft matured in its revised role, its story shifted from one of contested ambition to one of endurance. The bomber that had been conceived to sprint through hostile airspace at the edge of its performance envelope instead became a platform defined by persistence. This transition was not accidental. It reflected a broader realization within military aviation that adaptability often outlives raw capability. The aircraft's survival depended not on fulfilling its original promise, but on redefining its value. The modifications that followed were extensive. Structural reinforcements addressed fatigue concerns, extending the airframe's service life under less punishing flight profiles. Avionics were upgraded to integrate modern navigation, targeting, and communication systems. Precision-guided munitions replaced the nuclear weapons that had once dominated its mission planning. In this new configuration, the bomber became a workhorse of conventional power projection, capable of delivering sustained firepower with accuracy previously unattainable by heavy bombers. This evolution altered how the aircraft was perceived within strategic circles. No longer judged solely against the impossible standard of its original mission, it was evaluated on what it could reliably deliver. In conflicts where air superiority was established, the bomber excelled. Its payload capacity allowed it to carry large numbers of precision weapons. Its range enabled it to strike from distant bases, reducing reliance on forward deployments. Its endurance made it ideal for prolonged operations where persistence mattered more than speed. Yet the shadow of its origins never fully disappeared. The variable geometry wing remained a symbol of both ingenuity and excess. It was admired as a feat of mechanical design, but also questioned as an artifact of a design philosophy that favored complexity. Future aircraft would achieve comparable flexibility through aerodynamics, materials, and control systems without moving parts. In that sense, the bomber's wing represented both the pinnacle and the endpoint of a particular approach to aircraft design. The program's influence extended beyond hardware. It reshaped how large-scale aerospace projects were managed. Cost overruns, schedule delays, and shifting requirements forced policymakers to confront the risks inherent in pursuing multiple revolutionary advances simultaneously. Lessons were drawn about incremental innovation, about aligning design choices with realistic threat assessments, and about the dangers of anchoring strategy to a single technological assumption. Industrially, the aircraft left a durable imprint. It sustained a network of suppliers and specialists whose expertise would feed into later programs. Materials research, engine development, and systems integration efforts associated with the bomber produced knowledge that outlived the platform itself. Even in its perceived failure, the program contributed to the technological ecosystem that enabled future successes. Culturally, the bomber became an icon of Cold War ambition. Its silhouette, unmistakable and imposing, evoked an era when strategic competition drove nations to the edge of what was technically feasible. It appeared in documentaries, analyses, and debates as a symbol of both achievement and caution. To some, it represented the courage to attempt the extraordinary. To others, it stood as a reminder that ambition untempered by foresight can lead to compromise. The aircraft's operational record reinforced this duality. In conventional conflicts, it proved effective and reliable. Crews praised its stability, payload, and adaptability. Missions demonstrated that, even stripped of its original doctrinal context, the bomber could deliver decisive results. At the same time, analysts could not ignore that these successes occurred under conditions far removed from the environment for which the aircraft was designed. This contrast sharpened the lessons drawn from its history. The bomber showed that engineering excellence does not guarantee strategic relevance. It demonstrated that the pace of technological change can overtake even the most advanced designs. It illustrated how political, economic, and doctrinal shifts can redefine the value of a system long after it leaves the drawing board. In the broader arc of aviation history, the aircraft occupies a transitional space. It bridges the gap between an age dominated by speed and altitude and one defined by stealth and information dominance. Its story marks the moment when brute performance ceased to be the primary determinant of survivability. In doing so, it helped clarify the path forward, even as it struggled to follow it itself. The bomber's legacy is therefore not confined to its service life. It lives on in the philosophies it challenged and the alternatives it validated. Future programs emphasized reduced signatures, integrated systems, and modular adaptability. They sought to avoid the trap of over-specialization that had constrained the bomber's original concept. In this way, its shortcomings became as influential as its strengths. As years passed, the aircraft continued to fly, upgraded and repurposed, a testament to the resilience of its underlying design. It no longer chased the cutting edge, but it remained relevant through evolution. This endurance underscored a final irony. The bomber that was once criticized for excess proved capable of adaptation precisely because its foundation was so robust. The aircraft's journey from revolutionary penetrator to adaptable strike platform encapsulates a central truth of military aviation. Success is rarely absolute. It is negotiated over time, shaped by changing threats, technologies, and priorities. The bomber did not conquer the future it was built for, but it refused to be left behind by it. In the end, its influence is measured not by what it failed to achieve, but by what it taught. It revealed the limits of complexity, the importance of timing, and the necessity of aligning ambition with enduring strategic realities. These lessons would echo through subsequent generations of aircraft, informing decisions long after the bomber itself had faded from the forefront of innovation. In retrospect, the story of this aircraft resists any attempt at a simple verdict. To call it a failure is convenient, but incomplete. To call it a success is accurate only if the definition is allowed to evolve. What it truly represents is something far more valuable to the history of aviation, a moment of reckoning, when ambition collided with reality and forced an entire discipline to rethink its assumptions. The aircraft was born from a belief that performance could always outpace opposition. Speed would defeat radar. Altitude would defeat missiles. If one advantage eroded, another could be engineered to replace it. This mindset had defined decades of aerospace progress and had delivered extraordinary results. Yet the bomber exposed the limits of that philosophy. It showed that piling capability upon capability eventually produces diminishing returns, especially when the environment itself is changing faster than any single platform can adapt. This realization did not come cheaply. It was paid for in cost overruns, political controversy, and strategic uncertainty. But it was also paid for in knowledge. The program demonstrated, with undeniable clarity, that complexity is not free. Every additional degree of performance carries hidden costs in maintenance, logistics, training, and long-term sustainability. The aircraft could do remarkable things, but it demanded an equally remarkable ecosystem to keep it viable. That imbalance became impossible to ignore. At the same time, the bomber validated the enduring value of engineering excellence. Even as its original mission eroded, the aircraft did not collapse under the weight of its own ambition. Its structure proved resilient. Its systems, though demanding, were fundamentally sound. When doctrine shifted, the aircraft adapted. It found relevance not through dominance of the threat environment it was designed for, but through versatility in the one that replaced it. That adaptability is not accidental. It is the product of rigorous design and uncompromising standards. Operationally, the aircraft's later career revealed a different kind of success. In conventional roles, it delivered sustained precision at scale. It demonstrated that payload, range, and persistence still matter when air superiority is achieved. It became a platform that could influence conflicts not through shock alone, but through endurance. This was not the future its designers envisioned, but it was a future that justified the aircraft's continued existence. The socio-economic impact of the program cannot be separated from its technical legacy. Tens of thousands of skilled jobs were created and sustained. Entire supply chains were built around its production and support. The knowledge generated during its development flowed outward, influencing materials science, propulsion, avionics integration, and large-scale systems engineering. Even critics of the program benefited from the expertise it preserved within the aerospace industry. Politically, the aircraft became a catalyst for reform. It forced decision-makers to confront uncomfortable truths about procurement, accountability, and long-term planning. Future programs would be judged more harshly for cost growth and misaligned requirements. Incremental development, modular upgrades, and clearer threat alignment gained prominence in response to the lessons this bomber made unavoidable. In this sense, its struggles reshaped not only aircraft, but institutions. Culturally, the bomber occupies a rare position. It is simultaneously admired and questioned, respected and scrutinized. Its silhouette evokes power, yet its history invites caution. It stands as a symbol of an era when nations believed that technological audacity alone could secure strategic certainty. The fact that this belief was challenged does not diminish the courage behind it. It gives that courage context. Perhaps the most enduring lesson of the aircraft is that timing is as decisive as innovation. The bomber did not fail because it was poorly designed. It faltered because the world changed around it. Defensive technologies advanced, strategic priorities shifted, and stealth emerged as a fundamentally different answer to the same problem. The aircraft arrived at the edge of a transition, optimized for a reality that was already giving way to another. In aviation history, such moments are pivotal. They mark the boundary between eras. The bomber became the final expression of a design philosophy rooted in speed, mass, and mechanical adaptability. What followed emphasized invisibility, integration, and information dominance. Without this aircraft, that transition would have been slower and less certain. Its existence clarified the path forward by revealing what could no longer be relied upon. For engineers and strategists alike, the aircraft story offers a disciplined form of humility. It shows that brilliance does not guarantee permanence, and that success must be measured against a moving horizon. It reinforces the idea that the most important contribution a system can make is sometimes the lesson it leaves behind, rather than the dominance it achieves. As the aircraft continues to fly, upgraded and repurposed, it serves as a reminder that legacy is not static. Meaning evolves with context. What began as a symbol of uncompromising penetration became an example of strategic adaptation. What was once criticized for excess became valued for reliability. This transformation does not erase the past, it completes it. In the end, the bomber's narrative is not one of wasted ambition, but of ambition refined by experience. It illustrates that progress is forged not only through triumph, but through confrontation with limitation. Aviation advances because engineers dare to push too far, and then learn where the edge truly lies. The history of aviation is written with steel, ingenuity, and the will to challenge limits.